Multiplying and dividing square roots. Also, we're going to take a look at the Pythagorean Theorem. So far, we have multiplied roots. We've taken root 2 times root 3 and gotten root 6. I want to point out that since you can multiply roots, you can also divide them. Take a look at this example over here. 2 times 4 is 8. That also tells us that if I take 8 and divide it by 4, I get 2. Or if I take 8 and divide it by 2, I get 4. The same thing applies here. If I take root 6 and divide it by root 3, I get root 2. If I take root 6 and divide it by root 2, I get root 3. It works then just the way you think it ought to. The square root of 30 divided by the square root of 6 is the square root of 5. The square root of 14 divided by the square root of 2 equals the square root of 7. Be aware, though, that they both have to be roots to divide them, just like they both have to be roots to multiply them. If I ask you to take root 15 and divide it by 5, you can only approximate that. There's no way to divide that and get a nice answer. If they were both roots, then yes, you could do it. The answer would be root 3. But that's not the case here. This is actually the simplified answer. They both have to be roots to divide them. You can mix and match, though. If you had 24 root 22 over 32 root 11, I could divide the whole numbers both by 8, and I would get 3 and 4. And root 11 divided by root 22, I can divide them both by root 11, and I get root 2 here. This ends up being 3 root 2 over 4. If we had 18 root 20 divided by 27 root 5, we could divide the 18 and 27 by 9, and we would get 2 and 3. Divide both of these by root 5, and we get root 1, which is 1, and root 4, which we can also do. So this is 2 root 4 over 3 root 1. Notice that 3 root 1 is 3 times 1. The square root of 1 is 1. That's 3. The square root of 4 is 2. This is 2 times 2, which is 4. And the answer is 4/3. 28 root 14 divided by 21 root 2. I can divide both of these by 7, and I get 4 and 3. I can divide both of these by root 2, and I get root 7 and root 1. The square root of 1 is 1. This is 3 times 1, which is going to be 3. And up above, we will have 4 root 7, 4 times root 7. You'll notice on the previous page, I didn't include any examples that had square roots in the denominator as an answer. That's because we don't normally leave square roots in the denominator of a fraction. It's part of simplest radical form. We remove any radicals in the denominator. This is called rationalizing the denominator. The way we rationalize the denominator is we make a 1 using the denominator. If I had 8 divided by root 2, I want to remove that square root from the denominator. All I do is I take the root 2 and I make a 1 with it. Then I multiply straight across. 8 times root 2 is 8 root 2. Root 2 times root 2 is root 4. Think about why that worked. When I multiplied the top and the bottom, the numerator and denominator, by root 2, by the way, root 2 divided by root 2 is 1. I'm multiplying by 1. It's not going to change the value of our fraction. The reason this works to eliminate the square root in the fraction is what we just did was create a perfect square. Root 2 times root 2 is root 4. That's a perfect square. I can take the square root of 4. It is 2. This is 8 root 2 over 2. Now I need to point something out. There's multiplication right here, and that turns out to be important. Notice that if I take, as an example, 3 times 7 divided by 7 is 21 divided by 7, which is 3. If I cancel those 7s, I can see the answer is 3. That works because there's multiplication right here. Multiplication is what allows us to cancel. That's what we have up above in 8 root 2 divided by 2. I've got that multiplication allowing me to divide both by 2. 2 divided by 2 is 1. 8 divided by 2 is 4. This is 4 root 2 divided by 1. Anything divided by 1 is itself, so it's just 4 root 2. This is a bit odd if you think about it, because 8 divided by root 2 turns out to be the same exact thing as 4 root 2. This is a much nicer thing to work with, which is partially why we rationalize the denominator. The other reason we rationalize the denominator is so that we all have the same answer. We all recognize the same answer. These two things are really the same decimal. Is it easy to tell that? Not for most people. So remember, anytime we have a square root in the denominator, we rationalize the denominator. We make it a rational number. Square roots are irrational. We make it a rational number. In this case, it was 1. Let's do a couple more examples. If I had 15 divided by root 3, I have a square root in the denominator. We're not going to leave that in the denominator. We're going to make a 1 with it. Whatever your square root is in the denominator, just make a 1 with it. Anything divided by itself is 1, and that won't change the value of my answer. Up above, I have 15 times root 3, which is 15 root 3. Below, I have root 3 times root 3, which is root 9. I now have a perfect square in the denominator. This is 15 root 3 over the square root of 9, which is 3. I have that multiplication that allows me to cancel. I can divide these both by 3, and I get 5 and 1. Anything divided by 1 is itself, so the answer is just 5 root 3. If my question was 10 divided by 3 root 2, I only need to eliminate the root part. Make a 1 with that root part. I'm multiplying by 1. That's not going to change the value. I get 10 root 2 over 3 root 4. This is 10 root 2 over 3 times 2. Square root of 4 is 2. This is 10 root 2 over 6. I could have canceled right here, divided by 2 and divided by 2, but I can also do it here. Divide by 2, you get 3. Divide by 2, you get 5. My answer is 5 root 2 over 3. Sometimes, when you rationalize the denominator, it doesn't make the answer any nicer, like in this case. 7 divided by root 5. Again, I just make a 1 with that root 5. This is going to be 7 root 5 over root 25. I made a perfect square right here. And that's 7 root 5 over 5. And that's your answer. Be aware that 7 over root 5 is equal to 7 root 5 over 5. Those are equal. But we don't normally have this as the answer because we don't leave square roots in the denominator. This is the preferred answer, even though they are the same decimal. The last thing we're going to look at on today's assignment is the Pythagorean Theorem. The Pythagorean Theorem says that the sum of the squares of the legs of a right triangle, this is a leg and this is a leg, is equal to the square of the hypotenuse. The hypotenuse is the side that's opposite the right angle. The sum of the squares of the legs, that's a squared plus b squared, is equal to the square of the hypotenuse, equals c squared. Whole numbers that fit this pattern are called Pythagorean triples. The first of which is a 3, 4, 5 right triangle. The biggest side is always the hypotenuse, that would be the 5. And notice that 3 squared plus 4 squared is equal to 5 squared because 9 plus 16 equals 25. Any triangles in the ratio of 3 to 4 to 5 will also be Pythagorean triples. If I doubled every side and said 6, 8, 10, what you're going to notice is that 6 squared plus 8 squared is equal to 10 squared because 36 plus 64 equals 100. If I took a 3, 4, 5 and multiplied each side by 3, that would be 9, 12, 15. That's also a Pythagorean triple. 9 squared plus 12 squared equals 15 squared. They don't have to be in just the ratio 3 to 4 to 5, though. For example, if 5, 12, 13 is a Pythagorean triple because 5 squared plus 12 squared equals 13 squared. Because 25 plus 144 equals 169. Most of the time, though, when you use Pythagorean theorem, you get answers that aren't nice. Sometimes we round those answers, but sometimes we want those answers exact, and that's why we have simplest radical form. What you're going to do on this assignment is solve for some different side lengths and put them in exact form, that simplest radical form. And you're going to use the formula a squared plus b squared equals c squared. A and b just have to be one of the legs. I could switch them back and forth. That makes no difference. But always c is the hypotenuse, and it's the biggest side. It's always opposite the right angle. Here then, a squared plus b squared equals c squared is going to be x squared plus 10 squared equals 16 squared. We're going to solve for x. X squared plus 100 equals 256. We'll take 100 off each side and get the x squared by itself. X squared equals 156. Now we need to find the largest perfect square that divides evenly into 156. Start at the beginning. Remember, 1 isn't very useful here. We got to start at 4. Does 4 go into 156? Go to your calculator and divide. It does. It goes in 39 times. So to solve for x, I'll take the square root of both sides. The square root of x squared is x because x times x is x squared. 156 is 4 times 39. Remember, this is under the square root. I'm going to take the square root of 4 and it's going to go out front of the root. It'll be a 2. Left underneath is 39. Now 39 is 3 times 13, and both of those are prime numbers. There's no more perfect squares than 39, so my exact answer for the side length I'm looking for is 2 root 39. If you're looking for more examples of the Pythagorean theorem and finding exact answers, go to the end of the video. It's in the last couple of questions. The rest of this video is questions from your assignment. These first couple are review. Multiply. Root 5 times root 15 is the square root of 75. We're going to write this in simplest radical form. we need the largest perfect square in 75. Remember that you can find it by looking at the two things you're multiplying and finding that greatest common factor. There's a 5 here, and there's also a 5 and 15 because there's 3 times 5. Those two 5s, 5 times 5, is going to make a perfect square of 25. 75 is 25 times 3. I can take the square root of 25, it goes out front, and that would be 5 root 3. Question 4. 6 root 7 times 9 root 21. This is going to be 54, 6 times 9, root 7 times 21 is 147. We need to find the largest perfect square in 147. We can spot it right here. The GCF of 7 and 21 is 7. There's a 7 and 21, 3 times 7, and there's a 7 right here. Those two 7s are going to make a perfect square of 49. This is 54 root, and 49 times 3 is 147. I can take the square root of 49. It goes out front as a 7. There's multiplication right there. 7 times 54 is 378. So my answer is 378 root 3. Question 7. Students always want to make this complex, but just remember what squared means. Root 3 squared is root 3 times root 3, which is root 9. What's the square root of 9? 3. Oh, look at that. Question 8. 7 root 2 quantity squared. That's 7 root 2 times 7 root 2. Take 7 times 7, that's 49. Root 2 times root 2 is root 4. What is the square root of 4? 2. So this is 49 times 2, which is 98. Find the square root in simplest form. This is the first one we've had just like this. I want to point out that this is the same thing as root 4 divided by root 100. The square root of 4 is 2. The square root of 100 is 10. Both of those are even. Divide by 2, divide by 2, I get 1 and 5. My answer is 1/5. Now let's point out, if you go back to the beginning, 4 over 100, notice that both of these are divisible by 4. Divide by 4, you get 1. You're actually dividing by root 4. Divide by root 4, and you get 25. This then is the square root of 1 over 25. And I can split that up, the square root of 1 over 25, which simplifies to the same answer of 1/5. Question 10 and 11. As long as they're both roots, you can divide them. I can divide both of these by root 7. Anything divided by itself is 1. Root 14 divided by root 7 is root 2. And anything divided by 1 is itself. My answer then is root 2. Below, in question 11, I can divide both by root 3. Anything divided by itself is 1. The square root of 18 divided by the square root of 3 is the square root of 6. So this is root 6 over 1, which is root 6. And of course, you can just go root 14 divided by root 7 is root 2. You don't need to do that. Root 18 divided by root 3 is root 6. Question 12. 72 and 54 are both divisible by 9. We get 8 and 6. 8 and 6 are both divisible by 2. We get 4 and 3. Root 7 and root 70 are both divisible by root 7. We get 1. Anything divided by itself is 1. And root 70 divided by root 7 is root 10. What I have then is 4 root 10 over 3. Question 13. 12 and 33 are both divisible by 3. Divided by 3, we get 4 and 11. Root 65 and root 5 are both divisible by 5. We get 1 and 13. That's root 13. Notice below it's 11 times 1, which is 11. And above 4 root 13. And there's our answer. Question 15 and 16 are both rationalizing the denominator. What we do is we create a perfect square in the denominator. The way we do that is we take the root, whatever it is, we make a 1 with it. Root 2 over root 2. Then we multiply straight across. 10 times root 2 is 10 root 2. Root 2 times root 2 is root 4. The square root of 4 I can do, though. It's now a perfect square. I get 2. The square root of 2 is an irrational number. We've now made it a rational number. This is called rationalizing the denominator. Up above, I have 10 root 2 over 2. 10 and 2 have a common factor of 2. I can divide them both by 2, and I get 1 and 5. And my final answer is 5 root 2. Question 16. Take the denominator, make a 1 with it. Root 6 over root 6. This creates a perfect square in the denominator of root 36. Above, I have 12 root 6. This is 12 root 6 over 6. Both of these are divisible by 6. I get 1 and 2. And my answer is 2 root 6. Question 19 and 20 are also rationalizing the denominator. Make a 1 with your denominator, root 11 over root 11. Root 11 times root 11 is root 121. Above, I have 12 root 11. The square root of 121 is 11, and I have 12 root 11 over 11. Remember, you cannot cancel the root 11 and 11. They're not the same thing. The square root of 11 is 3 point something. Those don't cancel. They both have to be roots to cancel, or both have to be whole numbers or integers to cancel. Question 20. This is root 11 over root 14. I like splitting it up. I'm going to make a 1 with the denominator and multiply by root 14 over root 14. This is going to create a perfect square. This is the square root of 196, and 11 times 14 is 154, so root 154. The square root of 196 is 14, so this is over 14. And you might wonder if 154 has any perfect squares in it, because you should check. But notice that 154 was created by 11 times 14, which is 11 times 2 times 7. Those are all the numbers that make 11 times 14. Notice that there are no perfect squares there. This then is the answer. Question 21. Pythagorean Theorem. We know that it's a squared plus b squared equals c squared, where c is the hypotenuse. It's always opposite the right angle. There's my c. A squared plus b squared equals c squared will be x squared plus 8 squared. The order here makes absolutely no difference. You can flip that around, does not matter. Equals c squared. The biggest side is the hypotenuse, that's 12 squared. This is x squared plus 64 equals 144. We'll take a 64 off each side. We're trying to get x by itself. X squared equals 80. We can take the square root of both sides to get x. and we look for the largest perfect square in 80. Now I know that 4 goes into 80. Notice that it's 4 times 20. But 20 still has a perfect square in it. It's 4 times 5. And these two 4s will make a perfect square of 16. 4 times 4 is 16. 16 is the largest perfect square in 80. I'm thinking of 80 as 16 times 5. This is under the square root. The square root of 16 goes out front of the root as a 4. Left underneath the root will be a 5. 4 root 5 is the answer. Question 22. We have a right triangle again, and we know that a squared plus b squared, you can switch those two around, equals c squared. And c is always opposite the right angle. It's always the biggest side. So take your Pythagorean theorem and plug in your numbers. That would be x squared plus 13 squared, or you can turn that around, doesn't matter, equals 15 squared. That's x squared plus 169 equals 225. 225 minus 169 is 56. X squared equals 56. Pretty sure that 4 divides into 56. I'll divide it by 4 and I get 14. So I'm going to take the square root of both sides, and I know that 56 is 4 times 14. I can take the square root of 4, that goes out in front of the root as a 2. Left underneath is still the 14. 14 has no perfect squares in it because it's 2 times 7. And there's our answer. Question 25. Here we're trying to find the hypotenuse. That's the x right there. And that means in a squared plus b squared equals c squared, we're trying to find c. That's our x. What we have then is 3 squared plus 12 squared. Remember, these two can be turned around. It doesn't matter which one you call a and b. Same difference. You're going to square them and add them. But c is always the hypotenuse, always opposite the right angle. This simplifies to 9 plus 144 equals x squared. 9 plus 144 is 153 equals x squared. Now the question is there any perfect squares in 153? You could use a factor table to figure that out, but if you know your divisibility rules, we can figure this out. The divisibility rule for 3 and 9, both the same, is if you sum the digits, that's 1 plus 5 plus 3, which is 9. If 3 divides the sum, 9, 3 will go into the number evenly. If 9 divides the sum, then it will go in evenly. Now, since those digits add to 9 and 9 divides into 9, 9 will divide into 153. So when we take the square root of each side, this turns out to be 9 times 17. And the square root of 9 is 3. That goes out in front of the root. We still have 17 under the root. 3 root 17 is the answer.